Hello and welcome back to AP Pre-Calculus. Today's lesson 2.10 is inverses of exponential functions. All right, let's talk about a graph of a logarithmic function. So earlier we talked about inverses, right? Inverses meaning you switch your x's and your y's. It's not an opposite idea, it's a switching idea. All right, so I want you to look at the graph of an exponential. So that's what a graph of an exponential function looks like. Like that, this is a basic one. We don't have any kind of transformations or anything. This would be a basic graph. And this point right here, if it was a basic graph, would be 0, 1. Now, think about what the inverse would be. Wouldn't that be 1, 0? So that point would be here. If you remember from an earlier lesson, we said that the graph would be reflected across the y equals x line, okay? So that looks like it cuts it in half a little bit. So our logarithmic function would look like this, okay? So exponential function, logarithmic function, they are inverses of each other. Also, if you recall in a previous lesson, for exponential functions, when we have an equal width in between our input values, meaning our x values, and the output would change multiplicatively, right? So if you look at our first one, I'm adding 2, I'm adding 2, I'm adding. So my x's stay the same. Here I'm multiplying by 2, multiplying by 2, multiplying by 2. And that is definitely... All right, let's look at example 1 here. Let's start with A. We want to determine if these are logarithmic, exponential, or neither. Remember, for exponential, x has to be equal, y's have to be multiplied. For logarithmic, the x's have to be multiplied, the y's have to be equal spaced. So let's look at our first one. 1, 2, 3, 4. These are all adding 1, so logarithmic is out. What am I multiplying by? 1 half, 1 half. Oop, that's a times. And times 1 half. This is exponential. Okay? Let's look at B. 10 to 30, I'm multiplying by 3. Multiplying by 3 and multiplying by 3. If the y stays the same, if we're adding the same time, add 10, add 10, add 10, this is logarithmic. See how that's easy? Let's see. Multiplying by 10, multiplying by 10, and multiplying by 10. Let's look at the y's. Adding 1, adding 2. Well, we can stop right there, but then we add 4. This is neither. Okay, it didn't meet either one of our criteria. Let's look at D. Multiplied by 2, multiplied by 2, multiplied by 2. And the other side, subtract 3, subtract 3, subtract 3. The y's stayed the same. They're equally apart. The x's are multiplied by the same thing over. This is a logarithmic. And I need to go back, and I was being kind of lazy on these. We got to be careful on our test that we don't shortcut too many things, because we don't want to lose points just because we've shortcutted a word that they don't want us to shortcut, all right? So make sure that you're writing out the full word. Don't be lazy like I was, because we don't want to lose silly points. All right, here we want to prove that two functions are inverses of each other. And if you remember when we did that earlier, we said as long as f of g of x and g of f of x, when you do those, you come up with x for both of those, that would be an inverse. Also, they are reflections over the y equals x line. And if one point x sub 1, y sub 1 is on the graph of f, then when I flip them, y sub 1, x sub 1 must be on the graph of the inverse function for f, okay? So let's look at example 2. So here we have, the first one is our exponential. F of x is 3 to the x. G of x is log base 3 of x. So the first one wants us to do f of g of x. Well, I know what g of x is what it is. It's the log 3 of x, okay? And then I'm going to put that into the f function, which is 3 log base 3 of x. Now, we haven't talked about this before, but you should have learned it last year in Algebra 2. When your bases match, so this 3 has an exponent, right? This is the exponent. So 3 is a base. This is a base. It's called log base 3 of x. When your bases match, they cancel each other out, so I'm left with x. What if I did it the other way? I know what f of x is. It's 3 to the x. That 3 is a base. So if I do log base 3 of 3x, this base and this base, they match. They cancel each other out. I'm left with an x. So they do both work down to x. If you really want to see how this works out, I could take my 3 log base 3 of x and set it equal to, I'll just use a question mark for now, right? So now if I want to rewrite this in log form, I would write down what it's equal to, all right? So this is my exponent, and remember, logarithms are equal to exponents, so I'm going to write equals x. Then I'm put log, what's the base? Well, 3 has the exponent, so that's the base, and I'm looking for here, right? So if log base 3 of something is equal to log base 3 of x, what does that something have to be? Well, it has to be the x, right? I could do the same thing over here. Log base 3 of 3 to the x is equal to what? Well, this one is written in logarithm form. I don't know what to do, so I could rewrite it in exponent form. What's the base? 3 to the exponent. Well, I don't know the exponent. I'm going to put a question mark there. Is equal to 3 to the x. So 3 to what power equals 3 to the x? That question mark has to be an x. And probably should have used a variable there. I could have used the b from earlier or whatever. But it doesn't matter. That's the math behind it. But I do want you to know that if the bases match, they cancel each other out, leaving whatever the exponent is. Okay? All right, so I already kind of showed you this on an earlier slide, but let's kind of formalize it up here. So first thing I would do on a problem like this, because what I want to do is I want to graph the inverse of my exponential function, right? It's a log base 2 thing. So I'm going to pick a point. I always like to start with a point, and I see that 0, 1 is a point. So I'm going to graph 1, 0. So I know I have to go through that point. Now I want to look what's going on with my graph. Well, as I'm approaching negative infinity on my x, I'm getting really close to 0 on my y. Well, let's flip that up. So remember, this is approaching negative infinity on x. Let's approach negative infinity on y. Well, if my y was approaching 0, then this one, my x will approach 0. So it's going to come down like this. Get really close to that, almost vertical, right? What about the other side of this graph? Well, as I'm moving to the right on the x, or positive infinity, I'm increasing without bounds. So now when I'm moving up, I'm going to be and really, I'm going to tell you, I would use some points here. I would use this point right here. If you see that point right there, what is that? 2, 4. Switch them up. 4, 2. So now I have a point, and this point right here, I'm right there. And then I can just make it like that. So that's how I would graph that. It's not a great graph, but it'll work in a pinch. All right, last example. So we have some exponential function. They didn't really give us a lot here. They said h of x is equal a to the x. But we do know that it contains the points 2, 3 and 6, 27. We want to find the average rate of change. We haven't seen that in a couple days. So let's write that down. Average rate of change. What is that again? That is our algebra slope, right? Just our change in y over change in x, meaning y2 minus y1 over x2. All these things that we've learned in the past, right? So they didn't give me a lot here, but they did give me 2 points. And what we do know is that a logarithm and an exponential are inverses of each other. So if these are inverses of each other, what is an inverse again? It's not the opposite. It's a switching idea. So I know that if this point goes with that, then I also know that 3 comma 2 must go with my logarithm. If 627 goes with my exponential, then 27/6 has to go with my logarithmic. And now I have a couple of y's and a couple of x's, and I can find the change. I can do 6 minus 2 equals 27 minus 3, or 4 over 24, or 1/6. And that would be our average rate of change over the interval 3 to 27.